Okay, please be comfortable. Okay, so uh, I have over 17 years of experience and have worked in various MNCs like IBM Canada, Wipro, and basically into the Java related technologies and around that. Right. Okay. So what we are going to cover in this session is basically on the left hand side, that is the containerization architecture, microservices architecture, inter-service communications, cloud-enabled data engineering, DevOps, DevSecOps, legacy application modernization, and hybrid cloud architecture. And if you see the agenda of this whole PPT, it cannot be covered in this 30 to 45 minutes of session, as you know, right? So what I have tried to do here is I have mapped all of these, which is on the left side, to the right hand things, right? So I have covered what are the current industry trends till 2023 in terms of the cloud architectures, right? The overall architecture of all of these, which are on the left side, what are the various architectural best practices that we follow, right? And what are the industry recognized architectural guides like the AWS architecture framework, the Azure architecture framework, and the Google architecture framework. Okay. We'll begin with the market trends. So as you know, life moves pretty fast in the cloud, right? And much faster when you compare it to the 12 months back. The cloud has constantly changing. The technologies are constantly basically improving. The new technologies are coming in, and we have to deal with all of these technologies at a pretty fast pace. So if you see the McKinsey report, it says that we are basically shifting from the public cloud to the private cloud and now to the hybrid cloud. By hybrid cloud means we have the on-premise architectures as well, right? And we have the public cloud as well, and they are basically connected to each other using the pairing or the subnetting process, right? So organizations are pretty fast moving towards the hybrid cloud infrastructures, right? Then with the increase in the number of smart devices, right, people are pushing towards the edge technologies and the hybrid technologies. So if you see by 2025, 95% of the new digital initiatives will be on the cloud. That is the report by the Datadog and the McKinsey. That says that the new digital initiatives will completely be shifted on the cloud, and that is 95% is a big number, right? Then with the innovations that are fueling in, right, the remote desktop applications, the artificial intelligence are coming into the DevOps processes, right? So these are all fueling the enterprises and the organization to move towards the cloud, right? Then if you see the McKinsey report again, the 2023 report, it says that the trends toward the serverless architecture is increasing, right? It's accelerating like anything, right? The use for Kubernetes as the orchestration framework, right, is fast accelerating. Then there's a group called AMG, which is Amazon, the hyperscalers, by the way, Amazon, Microsoft, Google. So they basically contribute, they're basically the main cloud providers, right? And they are minting around $180 billion a year by using their cloud services, right? And they are growing almost 24% annually, right? So these are big numbers that we are talking about. Okay. Now, when it comes to the cloud native applications, what is required for a cloud native application? So if you see on the left side, there's a cloud, right, in which we have deployed the applications. Then there are compute servers, there are databases, right, the storage services, and we have other cloud service providers as well. Then we have the internet, which is the internet facing applications, right? And basically the external users who are logging into our cloud applications. Then there are on-premises applications, right, which is internal users who are basically connecting to the public cloud using the peering technologies or the subnetting process. Then what we deploy on the cloud, right? We have our own digital solutions that we deploy on the cloud in the form of the containers or as a monolithic application on the virtual machines, and right. So that application contains the budget logic applications, the databases, the networking, the technology infrastructure. So how do you basically stitch a complete cloud solution? You can stitch a complete cloud solution by using all these services which are provided out of the box by any cloud service provider, like the container service, right? The container service means the ECS service on the AWS, right? So you can use the container as a service, as the cache solution. Analytics service, big data service, VPN services, right? Storage services, compute services, and the security services. So in order to develop a complete holistic cloud solution, you need all of these services along with your application binaries to be able to deploy on these cloud service providers and provide a complete cloud solution to the end users. Now, all of these things are taken up from the CNCF sites and all the McKinsey reports. So this is not my, right? They have basically defined all these definitions there. So what are cloud native technologies? So basically cloud native technologies are or applications are those applications which are built to leverage the services provided by these cloud services provider, right? So they are built this way that they can leverage in an optimized way to use all of these cloud services. So what are these cloud services? These are the containers, the service meshes, the microservices, right? The immutable infrastructures and the declarative APIs to exemplify these approaches. So they build the loosely coupled system using all of these technologies, right? So that the system becomes a kind of a manageable, observable, and a resilient application, right? And on top of it, if you add the automation as well, then it becomes a highly frequently or highly impactful application that can be deployed with a minimal toil. Means you can add automations like DevOps cycle, right, on top of your application, and you can deliver all of these applications in a quick manner, in a faster manner. So if you go back behind, some time back, right? So when you build those applications, you will have a kind of a release cycle over 3 months. You develop your code, then it goes through a release cycle. It takes 3 months for a particular feature to come out. When you are talking about the microservices, right? It is a continuous integration and continuous deployment process where you build your feature incrementally and you continuously deploy it on the production servers, right? So it's a fast, impactful, frequent changes that you can deploy using the cloud native applications. And then there's another thing called the cloud enabled applications. So there's a difference between cloud native applications and cloud enabled applications. Cloud enabled applications are basically those legacy applications which are not born for the cloud. They were old applications, but we basically tweak them in such a way that they become a cloud enabled, that they can be deployed on the cloud, but they will not be using the whole services or leveraging the whole services that is provided out of the box by the cloud. Okay. So you can say various Oracle applications, various SAP based applications, all those legacy systems which are used in the banking systems for long years, right? So they are not built for the cloud. So what we do is we basically tweak them or customize them little bit so that they can become cloud enabled and they can be deployed on the cloud, but they will never be leveraging the whole services which is provided by the cloud. They cannot be kind of auto scaled, right? So they are huge system like JD Edwards system. If we talk about it's a huge system, it's in 140, 150 GB system, right? When we deploy it, so you cannot auto scale them the way we do it with the microservices. Okay, so key building blocks for any cloud native application is first is the microservices, right? So microservices basically is a single unit of application. What we generally do is we build the whole process, right? A single process should be contained in a single microservice, and can be an AI/ML service, it can be an IoT or a gaming application or a blockchain application or a simple Spring Boot application as well. But the idea behind it should be granular in nature, right? It should have one function or one feature completely built into it and not dependent on other applications, right? And we deploy it onto the cloud as a container. So when we deploy it as a container, as an isolated environment, right, So it contains a microservice, right, which is basically business logic that is they're packaged in a container, and all their libraries, right? So when we say about talk about containers, containers are isolated environments. They contain their whole operating system process and everything inside package as a software package, right? And we can deploy that as a these microservices as a container on the cloud. Then we have a kind of an declarative APIs. Declarative APIs means there are basically two kind of APIs that we talk about. One is the declarative API, and the other is the imperative APIs. So what are declarative APIs? Declarative APIs are like Terraforms, Ansible, right? That we use because these are already defined. What we do when we want to provision some kind of infrastructure on the cloud, we use these Terraform scripts and we pass on that information to them. So scale up these number of EC2 instances for me, right? So we use these declarative APIs in the cloud environment for scaling up or provisioning the infrastructure in the cloud environment. Then we have the imperative APIs. Imperative APIs are the microservices, right? They are request response life cycles where we are that involved when we have multiple number of requests and we have greater number of responses, right? So these are imperative APIs. Then in order to have these containers properly work in the cloud environment, we need to have some kind of a management and orchestration system. That is the Kubernetes here. Why? Because we are showing here only 2 containers, but in a cloud environment there can be thousands of containers, right? And thousands of containers are running in an isolated environment, each in its own environment on the worker nodes, right? So in order to manage them, right, in order to stop them, start them, kill them, right, manage their life cycles, in basically integrating with them with the storage volumes and all that stuff, we need some kind of a mechanism to handle all these things. So there comes the Kubernetes orchestrations, right? So there are many tools that are built to manage the Kubernetes orchestration. For example, a Google Lens system. If you are talking about the AWS, we can use or leverage the Google Lens. In Red Hat, there's a system called OpenShift Clusters, which is an orchestration container platform. From their UI, we can manage all of that is deployed in the form of containers on the cloud systems. Then there's a service mesh. So service mesh is upcoming, right? So what a service mesh does is it basically creates a shadowy kind of an infrastructure layer around our pods, right? So if there are multiple number of pods are running, right, so it creates a kind of an infrastructure layer where we have a proxies running and basically communicating with each other. There's an inter-service communication going on. So what is it helping us with? It is helping us with that we are basically offloading all the communication related things to these service meshes, right? And the microservices are only concerned about the business logic that they are implementing, right? So what usually happens is if you want to have a communication between 2 microservices, inter-service communication between 2 microservices, you need to have some kind of an interface, right, which will make a call to the B microservice, right? So that is a communication thing that is happening in the inter-service communication between 2 microservices. When comes the service mesh, what it does is it offloads that communication thing to itself, right? So it will, in a proxy, it will make sure that all of the pods will have the proxies, and proxies will be communicating with each other, right? So it will basically offload that communication thing to the service mesh. Apart from this, it also gives you the flexibility of giving you the logging mechanism, observability, kind of traffic load management, right? So all of this can be handled in the service meshes, and the microservices will only be concerned or about the business logic that it needs to implement, right? So we are basically making it a lot more lighter microservice as compared to the earlier ones. Then there's an immutable infrastructure. By immutable infrastructure means once these applications are deployed on these worker nodes, these worker nodes, if you want to apply the patches and all of that on these worker nodes, on the microservices which are scheduled on these worker nodes, right, we cannot change them, right? So these are immutable in nature. So in order to, and if you talk about the previous deployments, right? So in that cases, you can apply the patches to these machines. But what happens is it can also impact your application, right? Because you are applying the patches in the live environment on the operating systems, right? So it can impact your applications. But when you come talk about the cloud native applications and cloud, these infrastructure should be immutable in nature. So if you want to have the another feature or patch deployed on these infrastructure, you need to basically switch those microservices to the updated infrastructure, right? Then we have the hybrid clouds and on-premise data centers, which are connected with the public cloud, I said, using the peering mechanisms. Now, let's move to the containerization best practices and the market trends. So if you see here, the gist out of it is that according to a report by Datadog, you will be surprised to know that there are about 1.5 billion containers that are currently running in the production environment. 1.5 billion containers, right? That's a huge number, right? Then almost half of the containers, around 45% of the customer containers are developed in their own laboratories by these hyperscalers. By hyperscalers, that's the Omdia research. The hyperscalers are basically AWS, Azure, Microsoft, right? So these are the main hyperscalers or the cloud providers. Then people are increasingly moving towards the Kubernetes because they want the orchestration of those containers, right? And the big organization like the MySQL, MongoDB, Kafka, and all of them are coming up with their own containers, right? Because they are seeing that people are fastly moving towards the cloud. And the last one is almost 65% of the worldwide organizations have adopted the use of containers and Kubernetes. This is as early as 2023. So you can see it's pretty good time to move towards the cloud, right? Now, containerization architecture and best practices. So if I will be using a mix of Hindi and English. So okay, so we have the bare metal configurations, we have the VM instances, and we have the containers and microservices, right? So what are the differences between these three kind of systems, right? Bare metal configurations are the systems where we have the physical server, right, with the operating system, host operating system, app environments and their libraries, and the applications deployed on them, right? So what is happening here is the applications are directly communicating with the host operating system using its kernel and all of that stuff, if it's a Linux system, right? Where it is used where you need a fast computing, right? And on what kind of applications that are getting deployed, that are basically usually gets deployed on metal are the legacy applications. Right. So bare metal configuration, why? Because we have no kind of a intermediary here. The application is directly communicating with the host environment using the app environments, libraries, that stuff. Right. Then we have VM instances. So what VM instances are different and how they are different from the bare metal is that they have a specialized software called hypervisor, which gives you the virtualization technique. Right. So with the help of this virtualization technique, you can basically divide that physical server into number of VM instances, and all of those VM instances will have its own operating system, right? They have their own guest OS, right? And applications will be having its own libraries and the libraries which are there on the host operating system, and they can deal with each other, right? So these are the separation of VM instances, right? And the app 1 is not talking to app 2. Just they have their own isolated environment as a VM on one physical server only, which usually happens with when you get some kind of a virtual machine from Azure or as an EC2 machine from AWS. You get the VM machines only, right? So it is on the same physical server and you are getting the resource out of it. But they are using the resources of the same physical server. They're sharing the resource of the same physical server. Then there is the containers and microservices. So here is the difference between the VMs and bare metal and the third one, the container and the microservices. So in containers and microservices, we have the host operating system, host servers, infrastructure, right? The there's no hypervisor here, right? So there are separations of VM. Here there is a separation of processes. So containers, as I said, it runs in an isolated environment, right? The microservices and its libraries, and it needs a particular kind of an engine to run over, right? Like the container engine software like Docker, which is run C at the end of the day, or the container D, right? These are the Docker engines on which the microservices runs. So here we have the separation of processes. So what happens in this case is that if a particular container goes down, right, only that container is going down. In case of VMs, if the VM is going down, anything that is scheduled on that VM, number of pods, I would say if there are 20 pods that are scheduled on a particular virtual machine, all of them will go down together. Here also it can happen. How? Here we have a kernel, right? Usually we have two different kind of workloads, like the microservices, that the Linux workload or the Windows workload. Usually the industry prefers a Linux workload, right? So I'm assuming that this is a Linux system, right? So the microservices are basically communicating with the host operating system resources using a shared kernel. So if a kernel goes down, then all of these pods will, or the containers will go down, right? So that is the only catch. Otherwise, these are fast as compared to the virtual machines. Though in recent times, on the VM instances, as well, if a lot of research that has gone into and innovations have come in, that they have more or less covered up these things. Then what should be the size of the container, right? So container size should be as small as possible. You should not keep too many things in a container, right? As part of a best practice. The second most important point is this container should not be run as a root user. Never ever run a container as a root user in your entire life, right? You run it as some other user. Why I'm saying this? In your orchestration framework, if any of your container, right, which is running as a root user, right, and somebody somehow gets access to that particular container, right, then he can easily move into the entire surface area and can destroy a system completely, right? So never ever run a container as a root user. Yeah. Now here is the typical way of creating a Docker file and creating a container, right? So we have a Docker file here, right, which has all the commands that this needed to create an image, right? So what is an image here? So when we run that Docker file using a Docker command on top of run C, we get an image, a container image, right? Which is nothing but different layers of the software components that are packaged together, right? And give us an image. So it contains all your own custom written code, which is the microservice, all the libraries that are dependencies of those microservices, all the system libraries that basically it contains inside a complete or a small Unix operating system, right? The container in itself, right? So it contains all of those libraries. And then when you run this container image, then it runs on the application environment as your application, right? So you can think about it as if you have a Java class, which is a blueprint, right? And when you instantiate an object of a Java class, it becomes a runnable application, right? So you have a image, which is basically a Java class. When you run it, it becomes the object actually realizes, right? So object becomes the container runtime environment, becomes a runnable component or an application that is running in the on the worker node in the cloud native environment. Then there is the container manifest files, right? So what is the container manifest file? It contains all the metadata information about the container. So metadata information means what are the different parameters that are needed to run this container, what are the commands or entry points, right? All of that information is contained in that manifest file. Then when that image is produced, right, they usually be pushed into some kind of a repository, right? We place our code in the GitHub repositories or the Bitbucket repository, right? The same way the images are placed in the some kind of a container registries. So out of the box, AWS provide its own container registries, right? Everyone should be knowing that AWS Azure also provided its own container registries. So we make those images and we push them into the registry, so that when the DevOps cycle runs, it will pull up that image from the registries and create an runnable application as a pod onto the clusters or the Kubernetes clusters, right, as an application. Then we have container engines, right? Container engines are the ones on which these applications run. So, for example, containerd, runc, which is of the Docker, containers orchestrators. And these are basically the key terminologies that I'm talking about right now. I will give you the detailed way of how all of these things work, right? Container orchestrators govern containers. Kubernetes is the prime example. We have kind of a open source or a free trust containers, orchestration containers as well, like the Nomad or Cycle.io, right? You can leverage those as well, apart from using these. And the container host, basically the processes that are running on that particular host are the container host. Okay, this is typically, I've kind of erased these best practices because I'm going to tell you about all of them, right? So there's a DevOps pipeline that is going on. We have a code is getting built, tested, image is getting produced using the DevOps cycle, and it is getting pushed into the container registries. And then these containers registry, the DevOps cycle is pulling up those images and running it on the Kubernetes cluster, right, as a container which has a microservices and its database. So this is a complete DevOps life cycle, right? So in these, when we develop these containers, so as I said earlier, we need to take care of certain best practices. Like we have to have a shift left process. Shift left process means you need to secure your containers as early as you start developing it. You start writing the code, right? By securing the container, I mean to say that you should never be putting your configuration as part of your container logic or a business logic. Configuration should always be outside of your container, and it should be governed from some centralized third-party thing, right? And not from inside the container, right? Why I'm saying this? Because if you put, for example, I'm currently developing a container which is going to be deployed in a dev environment, and I'm putting those dev environment configuration in my container, right? And now I need to propagate after testing and all of that. So I need to propagate to the testing environment or to the higher environment, the production environment, right? If I want to take it to the higher environments, now if I have to change the code again, because the configuration is all tightly coupled inside my container logic, right? Or the business logic. So I need to change that again and build that container again for the another environment. Then after doing that, if I need to take it to the production, then I'll again have to change those configurations, right? But that is why I'm saying if you are building a container, you should never be putting your configuration things inside the container. If I give you an example, I am developing a Spring Boot application. I have written something in my application.properties file, which is getting picked up and getting deployed, right? There's a URL for the dev environment. Then as a container, it runs, right? When it becomes an image, right? So you can override these configurations using the Kubernetes config maps, right? So there's a precedence that goes on. And what is that precedence is that whosoever at the top and managing the whole orchestration, if there's some kind of a configuration mechanism there, if it is there, then that takes the precedence, right? So what I'll do is, if I have written a JDBC URL in my application.properties, I will be able to override the value inside that JDBC URL from my config map when that image gets deployed into the production environment or the test environment. So in the Kubernetes clusters, I will have I will have a config map for my test environment. I will have a config map for my dev environment. I will have a config map for my production environment. So all of these are three different Kubernetes clusters that are running on which the applications are getting deployed. So config maps takes precedence, and they will have a JDBC URL, which will have a testing URL. The production will have a production URL. So when this image gets deployed, and since it is not having the configuration inside it, it is having the local configuration which when you are developing the code, it gets overridden by these config maps. So you will never face that kind of a problem where as a human error, right? You mistakenly put the test URL into your production image, right? So always a config map is there at the top level, which will be overriding the values which are there in the application.property as a key. So that key should be there in the config map of the Kubernetes cluster. Okay. Then again, the most important thing is that we should never be running the containers as the root user, right? So these are basically two main practices that we should always be following when we are developing the containers. Okay, so this is typically the containers life cycle where we have a Docker file. Docker file now gets converted into an image. Image is now pushed into the container repository, right? And the container is deployed in an application environment. These are two microservices that I've shown here, right? So what can happen to these containers? These containers, when they get deployed on the worker node, they are into basically the running stage, right? So green is depicting the running stage. We can also, using the Kubernetes cluster orchestration platform, we can stop these containers. So we can pause these containers and we can also kill these containers. So what are the differences here, right? When we pause the container, we are basically saying all the instructions will not be executed anymore. We are in a pause state. But when we say we have stopped the container, it means that the memory is all cleared, right? The container is no more working. The memory is all cleared. Stop can be resumed. Pause can be resumed, right? The instructions can again, you can again start invoking those instructions. But when we say stop, that means the memory is completely removed. Now we cannot execute that container. And killed is when we completely remove the container, terminate the container. So there are chances that there's some kind of a bug or a problem in a container that is running in our environment, and we need to quickly terminate it. So when we terminate it, its reference is no longer the worker node. It's completely killed or terminated. Okay. Best practices in operating containers. So the same mechanism, right, that we were showing earlier. What we need here is basically the important thing is the persistent data stores. So when we say microservices, right, so each as part of the microservices architecture, we should have each microservices linked to its own databases, right? That is what the architecture says, right? That you should have a microservice should not be dependent, all of the microservices should not be dependent on one single instance of a database server, right? We should have the microservice and its own database. It should deal with its own database, right? So we should have the persistent data stores, right? Then we can also have these application environments, right? When the user uses and deploys these applications, the application environments, we can have those APIs, that is the Terraform and Ansible, that can be used or leveraged to deploy the different kinds of applications onto the application environment. Okay. Now comes the factors that drives the choice of container management and orchestration systems. Right. So if you see down here, we have infrastructure provisioning, right? And we can have the container services. So if you see, you make your own custom code, create a container and deploy it. But there is also other way of doing it. That is, they are the cloud providers are giving you the container management system as a service as well, which is called as a container as a service, right? So you can use the CAS system to deploy your custom code, right, as part of the container as a service. So basically, you are using a managed services which is provided by the cloud provider to deploy your code. So there are two ways of doing it. One, either leverage the managed service provided by the any cloud provider, or develop your own custom code, write a container, create an image, and deploy it as a pod in the application environment. Then, in order to manage all those containers, you need to have the container orchestrations and advanced management systems, right? Okay, so options for orchestration tools. If you want to use the custom things, right, you can make use of the cycle.io or Nomad orchestration frameworks. They are Kubernetes orchestration frameworks only. Let me just quickly go through it now. Okay, this is Kubernetes cluster, right? So architecture. So what are the important keynotes here is the pods, nodes, and clusters. So pods can have multiple number of containers, right? Why multiple number of containers? Because you never want your containers to run as a single system resource. So if you have thousands of containers, right, you will have using these thousands of system resources, right? So generally, we prefer to have tightly coupled containers residing in the same pod. So pod can have multiple number of containers. So I have a utility container and I have a microservice based container. And microservices is dependent on that utility container. So we can package both of these containers in a single pod. Container obviously contains a microservice in the libraries, and on these pods are getting scheduled on the worker node, which is called as a node or a worker node, right? These are all part of the Kubernetes clusters where we have the master node and the number of worker nodes, and all of them interacts with the control plane. Okay, so control plane is basically the brain of it, where we have the etcd scheduler and all that, and it takes the instructions using the master node and pass it on to the worker nodes, right? So it basically works as a front end to the Kubernetes clusters. Okay. Then this is the same thing. I'm skipping few slides now in the interest of the time. Okay, inter-services communications. I'll quickly go through the 4 things here. Okay, so in database issues in cloud native applications, how are we going to implement the multiple number of microservices, right? So all of these microservices will have its own data type. You can have the MySQL data, relational database management systems. You can also have the graph databases like the Allegro Graph, your InfoGrid, and you can have the key value databases like the Cassandra, Redis, or the DynamoDB, right? When we have the distributed transactions that are happening in the distributed environment where multiple number of microservices are there on the clusters, right? We can implement, in order to have the data consistencies, we can implement the Saga pattern. Saga has 2 different flavors. One is the orchestration, the other one is the choreography. Then we can have the API composition patterns, right? The CQRS, and there's the entire patterns as well. The entire patterns are shared database per service pattern, because microservice architecture says that you should have a microservice and a database, right? Its own database. But this particular pattern is the entire pattern, because it is saying that multiple number of microservices can have the same database, right? Then you can also have the multi-model database. So multi-model databases means that your microservices want to interact with the RDBMS as well as the graph as well as the key value databases. So you will define different number of models, right? All of these models will have a graph database, a Redis database, or a RDBMS database. So it depends what is your use case. Based on that, you prefer which database you would choose. These are the 12 principles of microservices, which are pretty much there on the internet. Cloud inter-service communications. Okay, let me just quickly go through these as well. So there are synchronous communications, right, where one microservice depends upon the other. And then there are gRPC, which is the backend inter-service communication, which is based out of HTTP2, which is, if you have worked 10, 12 years back, there are EJBs, right? So EJBs creates a stub and a skeleton, the stub at the client side and the skeleton at the server side, and they communicate with each other. Like if you're calling a method on the remote server, right, you call that method as if you are calling it in your own local JVM. So that is a kind of implementation, that is the gRPC, but it comes under the synchronous patterns only, but it does not use JSON. JSON is quite verbose. It uses the proto buffers, these binaries. So it communicates using binaries. That is why it is preferred at the backend inter-service communication. It is not at the front end, because browsers till now do not support the HTTP2. Right? If they are supporting the HTTP, we would have implemented the gRPC as well. LinkedIn has migrated to gRPC. There are 50,000 endpoints migrated to gRPC only. Then asynchronous communication, which is AMQP based message queuings, like RabbitMQ, Kafka. If you have a system where you have to consume 10,000 requests per second, you can use RabbitMQ. 1 lakh, you can use Kafka, right? Okay. API gateways, quickly. Why API gateways? Because in orchestration platform, from client to the server, you will have multiple number of round trips, right? Point to point. So in order to avoid those round trips, you put in API gateway. That is a centralized system from where you will route the request to the backend systems, right? Examples: Google, APG, Microsoft. Basics of gRPC, as I said, this is just an example where I'm showing the on the client browser, gRPC stub is there, and it is calling onto the server. The client makes a request, remote procedure call request, results return, but it waits, like it waits in the event looping as well, right? When you click on the Android applications and all that stuff. gRPCs, where you can use it where you need to have the low latencies. Asynchronous communication, you will raise an event in the message queue, and it's two ways. You can have a one-to-one queue implementation, like in the RabbitMQ, and you can have a topic kind of where consumer groups are there and listening to that particular topic. That is the Kafka implementation. And the other examples are Amazon SNS, SQS, MQ, Kafka, RabbitMQs. Service mesh, as I said earlier, it will create a proxy, a sidecar, which is a shadowy infrastructure layer, right? And it will communicate with each other using this inter-service communication pattern. Main examples are Linkerd, Envoy, AWS App Mesh, Istio, etc., etc. This I'm skipping DevOps. So DevOps lifecycle, the main difference quickly. Minutes. One is the continuous integration, right, where you are basically writing the code and continuously integrating it. There is a difference between continuous delivery and continuous deployment. Continuous delivery is that when you deploy your code till the staging environment, and then you wait for someone to approve it. So when someone approves it, then you take it to the production. And continuous deployment is when you are so much confident of your system that there's nothing wrong and everything is tested, then that you basically develop an automated DevOps cycle, and from that you will have a continuous deployment till the production. But that is the main difference between the continuous delivery and continuous deployment. Then you can use infrastructure as a code, right? The various registries, AWS code deploy, container registries, Terraforms, and a complete life cycle. The hybrid clouds, and these are the architectural frameworks, right? AWS Architecture Framework, Microsoft Azure, and CNFC recommended journey to cloud natives that you can leverage anytime. That is all there on the AWS and Azure side. Thank you. So you can scan it if you want and provide us.